Right. So our next speaker is Dagmar Sternad. She received her bachelor um, bachelor diploma from the TU Munich in movement science and linguistics. All right, and her PhD in experimental psychology from University of Connecticut. She was professor at UPenn, and now she's a professor at Northeastern University and holds an appointment in the departments of biology, electrical and computer engineering, and physics. And her research is in computational neuroscience, motor control, and with a focus on learning and controls of sensory motor coordination in humans, right? So very excited to hear your talk, Dagmar. We cannot hear you, you're muted.
Good.
Yeah.
Hello.
Hello.
Okay, so just put this down. So thank you very much, Roberto and the team. I want to talk today about, well, human control and learning of interactions with complex objects. And I want to use that topic to also show the kind of approach that we have developed over the years and more recently applied to the control of complex objects. So let me see how. There we go. So the scientific question, as I picked up from your description of the workshop, is, well, in casual formulation, how to get from pixels to torques. And that reminded me of how my doctoral advisor way back always talked about how does light get into the muscle. And this, of course, is the big topic, needless to say here, of perception and action and interaction. And how does the controller brain interact with the plant, with the body, or in terms of information processing, interacting with energy processing. And with Daniel's talk, I think we saw sort of a paradigmatic approach that emphasizes the information processing, whereas I will veer towards the energy processing. And we'll show you where and how we in our lab start to address this. So the common approach that you all know is we have, and I'm focusing on action and interaction. I happily ignore perception. I must right up front say that caveat. So as you all know, we start with hypotheses about the controller or the cost that the controller may then optimize for. We perform simulations based on assumed parameters. And then in the human science, we compare the human data with the model that we have developed. We have gone a slightly more, call it, agnostic approach, where rather than assuming a controller to be tested, we start with what we know, that is the task and the physics of the task. No parameters to be estimated because the physics dictates all of this. Then we continue to define execution and result variables, i.e. which variables are important for the execution of the action and what might be the result that is desired, which is not always clear when it comes to more complex interactions. With some minimal assumptions about the controller, specifically employing primitives that, again, in the robotics community is well known. We then move forward to test hypotheses, what might be the execution variable, what might be the result variable. And in these solution spaces, we can address both control and learning. So let me set the stage with a very simple task that I have shown many times. This is old work, but it's so simple that I think the approach will come through to then address more complex problems. Throwing a ball to a target, here Skittles, looks in our lab like this. We only have one target Skittle. We show the space in our virtual environment from a top-down view, such that the task itself and the action from ball release to hitting a target is very simple and described by very simple physics of the ball, which in our case is suspended by two orthogonal springs such that when we displace the white ball here away from that top-down view onto that center post, then when you release the ball with a certain angle and velocity, it traverses an elliptic path that gets close or hits the target with an error that is the minimum distance between the trajectory and the target. So also straightforward, once you start thinking about it, is that this is a redundant task because the two variables that determine the error, that is angle and velocity at release, the combination determines the trajectory. And actually, as in this graph, the red and the green trajectory is actually produced with different release angles and velocities, but both get zero error, whilst the blue dashed line has a non-zero error, well, with a different combination of angle and release. So analyzing numerically this task, we can set up what we call a solution space, where we determine the error at the target, shown in shades of orange, as a function of all possible release angles and velocities. So this is the space, a minimal space, agnostic about any control where this action takes place. Here specifically, that U-shaped set is the set of zero error solutions, such that the green and the red release on the left here has release points right on the manifold, whilst the blue trajectory is generated somewhere here off with a non-zero error. Now here and in subsequent more complex tasks, by doing this, we parameterize the action to be presented as a single point in a space, in a parameter space, where the result, error here, is a function of execution variables. This is the pervasive approach. Moving on, just take a quick look at how we then measure human performance here. The throwing action is performed by a subject using a manipulandum, passive manipulandum, and by holding the hand on a ball with a force sensor, by lifting the finger, you release the ball just as in a frisbee throw. And then, as you see simulated here, the subject can try all sorts of things, and we have examined learning in the following way, such that we again go into this solution space. Every trial is a point, and you see how over 3 days of practice, the data approximate that white solution manifold, zero error, and it approximates it as in sitting parallel, aligned with that manifold, such that we have formally used the space to examine learning by looking at the changes in the distributions and locations of that distribution of trials. We have quantified that in a way that calls translation, finding a tolerant area in this parameter space, rotation as a covariation with the solution manifold, and noise reduction as in shrinking the distribution. So this is how we approach both control and learning. Firstly, one more time, setting up this parameter space in which control happens, and then using it to examine learning as an exploration and call it optimization of that space towards the solution manifold. But now, let me emphasize one point. We show these U-shaped solution manifolds, they are determined by the target. But not only by the target, but also by the position of the manipulandum or the release position. And here we just move that pivot position of our manipulandum left and right, and you can see how actually this manifold changes in shape, i.e. we can, by choosing a position, actually design that parameter space, the geometry of that parameter space. And one more example where we have a second target up here, which drastically changes those solution spaces, and they change with the position of the manipulandum. So by reorienting your release towards the target, you design your solution space in which you then learn and control the task. So to actually look at that, not only in simulation, we did an experiment where here is again our virtual environment. And here the position of the manipulandum is fixed, meaning the pivot is fixed and only the forearm rotates. Whereas we replicated this skills task in real, back to what you saw earlier, right? We created a vertical pole and a target and a pendular ball where all the measurements were identical to what we represent in the in the virtual world. However, well, we prescribed the subjects where to release, but they were free to actually vary. So they could choose their release position. So first of all, who did better? Well, the virtual error over trials or blocks here is the virtual, which has higher error approximating the real improvement after 3 days. So despite the fact that there is a lot more to control, also the whole arm to control, the real performance is better. Now here we look as a top-down version, the release positions of the subjects, and these are 8 subjects in the first block and the last block, and you can see that the different subjects, they find different release positions such that they actually created their solution space. Here, the virtual throwing with a fixed release position, you see in those 3 subjects, here 1, 2, 3, that the manifold is always the same. And the data points on first block in red and blue on the later block, there is improvement, and it is pretty similar across subjects. Whereas here, where you can actually choose your release position, the manifold is different for each of the 3 exemplary subjects, and their solution is different. But overall, they are better. So the upshot is, what I want to show here is 2 things. Firstly, here is a summary of our approach, task dynamic approach. So we start by analyzing the task, which in this case is dominated by the dynamics of the ballistic flight, initialized by the execution variables, angle and velocity of release. And we only looked at one result variable, which is the error at the target. And by having the result as a function defined by the physics of the execution variables, we can set up different spaces like this and test our data and learning. Now, what we learned as scientists in this task is that indeed our subjects traverse these manifolds, these solution spaces, and they also can design them so that they are most compatible with their throwing preferences. Okay, task dynamic approach. Now let's move on to complex objects. And the complex object manipulation that I want to talk about is transporting a cup of coffee. It's a very weak coffee here, it's tea, I believe, but liquid, okay? Which is a highly nonlinear object with complex and unpredictable dynamics. So how on earth can we firstly say that we control an essentially unpredictable object? So what is the representation of this unpredictable dynamics that we are able to ultimately carry that cup of coffee without spilling the coffee? So our first overall hypothesis is that humans make interactions predictable. They make the object dynamics more predictable. So let's start with this very high level proposal and see how we can now use our task dynamic approach to actually quantitatively address this. So from the real task to a very simple model that we then represent in our virtual environment. So here is a first step that this three-dimensional object with fluid dynamics becomes a two-dimensional arc with a rolling ball inside. That's the kind of physics that I like. So we then go on and represent this ball actually as a cart moving on a straight horizontal line with an attached pendulum. And when you then only represent the bob and the spherical arc, then you come to exactly this kind of simplified representation. And this is what we then implement in our virtual environment, where subjects hold a robot arm and move that cart and pendulum, which they only see as a ball rolling in a virtual arc, and they manipulate and they get haptic feedback so that there is a true physical interaction. They exert force onto the cup, the ball exerts force back onto the hand, and in this interaction, they control and perform certain tasks that we ask them to do. The equations of motion of the object are here with one generic F interaction force that we will examine later. So first here is the task. Subjects are asked in this experiment to move the cup back and forth, listening to a metronome that specifies, in this case, a frequency of 1 Hertz. And they can choose their preferred movement amplitude. These are those very broad boxes so that they find a solution that is most comfortable to them. This is what we ask them. So before we analyze the data, let's first analyze the object. So we only look at the object and do inverse dynamics calculations, where the desired outcome is a rhythmic cup motion that is here and here with a given amplitude and frequency. That is, we fix the frequency and the initial ball angle, but we let amplitude vary, and the initial ball velocity is fixed, the frequency is fixed. However, we then do inverse dynamics by sweeping through all amplitudes here of the outcome cup position and initial ball angles. So 2 examples. Let's start with the right one here, where the input force or interaction force here is for that very simple sinusoidal outcome for a given theta 0 is already a superposition of several frequencies. In this case, with a different theta naught, in order to get this output, you have to put in a highly, highly complex input force, interaction force. So we summarize this sweeping through amplitude and theta naught by strobing this force profile at maxima of the cup position, and then use the marginal distributions, and we plot those for the given initial ball angle theta 0. This complex dynamics is represented here, and this simple dynamics is represented here. And by sweeping through the theta zeros, you can see what kind of interesting diagram occurs. Namely, this visually reminds you of a bifurcation diagram of, say, period doubling to chaos in nonlinear systems, definitely indicating chaos for certain parameterization. Chaos is essentially unpredictable. So here we have even our simple one-dimensional cart movement can, in essence, show chaotic dynamics. So how can we, as humans, actually control such an object? We hypothesize that humans seek predictability because feedback in humans is basically centuries for a roboticist, 200 milliseconds. So how do you use that feedback to error represent? How do you predict a model or an internal model for an unpredictable system? And we have noise. So our first simplified hypothesis is that humans seek predictability. We now take our simulated time series and we analyze them for 3 different hypotheses, or costs, you might say, what humans might optimize. Either predictability, quantified by mutual information between the input force and the object dynamics. We also looked at a mean effort solution, which in this parameter space of amplitude and theta naught looks like this, with an optimum here. Predictability has an optimum here. And we also looked at smoothness, which has an optimum even further away. Our data show very nicely how subjects actually verge towards that highest mutual information solution. So this first experiment gave us good support that predictability estimated in mutual information is a valid goal that our subjects have, and we can analyze learning in this space. I refrained from doing so, but rather go one step further. In a second experiment, which was exactly the same, only we reversed the instruction by saying amplitude now is fixed and they choose a preferred frequency. So our very first result, looking at what frequency subjects choose, showed in this histogram a very bimodal approach, suggesting that having 2 resonances with an anti-resonance in between, that actually we need to add a control input. Before we only did inverse dynamics. Now we are actually putting something into that force, interaction force. What we did in this first experiment is we used an input term, which was a sinusoid for the rhythmic movement, and we added an impedance to allow for lower level error corrections. Now, having this simplified control input, we can now define our execution variables and the result variable. Execution variables, we use the stiffness and the damping of the impedance portion, as well as the frequency that subjects were allowed to choose. This is what is under their control. As result variables, we used mutual information calculated as before, plus effort summed force. And here are our solution spaces that now allow us to test the hypothesis. What do subjects seek? Predictability and or minimize effort. Here is our 3-dimensional solution space with damping, stiffness, and frequency. And these pink areas here are mutual information values that are relatively above a threshold high. And each point, each blue point is an entire trial, evaluated, parameterized by its frequency, estimated stiffness value, and estimated damping value. And you see that the data lie smack in the high predictability area, whereas here the data are exactly the same, but the low expended effort is somewhere else and they're not there. So the data do not support that they lie in the low force solutions. All right, here is again, overview of our task dynamic approach. Now our task and the object is the object dynamics here, and we need a control input, which is either a bell-shaped velocity or a rhythmic input. That is rhythmic or discrete primitives connected via an impedance to the physics of the object. Our execution variables become other ones, and the result variables become other ones. So let me just briefly go through one more experiment, same thing, moving rhythmically. The only difference here is that subjects were allowed to choose, first explore the object, to choose their best initial conditions before they entered into this rhythmic back and forth motion paced by a metronome. So now we are looking at the initial conditions and hypothesize that the same hypothesis first, they establish a steady state with predictability. They reduce the transients by choosing initial conditions that achieve the predictable steady state faster. And third, they reduce risk by increasing a safety or energy margin. So initial conditions are now what we think is really at the core of what subjects control. So execution variables are the initial conditions, specifically the ball angle, ball velocity, and cup position. So very briefly, subjects establish predictability. Firstly, they actually do converge over trials to an initial ball angle. They do converge to an initial ball velocity and an initial cup position. And here, first hypothesis, they establish a steady state with predictability. Mutual information increases over trial. So hypothesis 1 is supported. Yes, predictability increases. Next is we examine transients, and not going into detail here, we can establish how long they are in a transient state before setting into a steady state where the phase difference between ball and cup is at a constant value. And these transients go down. The next hypothesis is that they increase the energy margin, here computed as an energy term where we have the threshold energy where the subjects lose the ball and the difference in energy between that threshold energy and the actual ball energy. This also increases, although it levels out. Okay, final point here. What is our control input? This is what we just tested above. That is a sinusoidal input with an impedance term. Or we actually also tested to what degree the impedance term with a sinusoidal desired XX dot is sufficient. And now we can test different result variables and different energy or control inputs. Control input 1 is with a sinusoidal input, 2 is impedance only. Predicting transient durations gives us spaces like this, and we can plot and see whether the data then actually end up at the optimum place here in dark blue. And secondly, we can look at to what degree our parameterized our solution space with a given control input predicts low energy margins, and here indicated by the lighter yellow space, which is a lot more spread out and not as focal above. So this is hot from the press. We are in the process of interpreting all this. So let me summarize here. What did we learn? When controlling an underactuated object that is essentially unpredictable, humans seek to make the object dynamics predictable. Subjects explore the dynamics of the object to shorten transients and establish a predictable steady state. They increase the energy margins, but only to a point. And our task dynamic approach allows us hypothesis-driven insights into this very complex continuous control task. And maybe just a final look at this whole framework. Our task dynamics here, the physics. Here we have minimal control input with primitives, rhythmic and discrete primitive and an impedance. We can hypothesize execution and result variables and then look at different spaces that we create to then actually find what is relevant for subjects. Okay, I will conclude with a big thank you to my crew here, our action lab. And in particular, I want to thank Sharan Zhang, who has done a lot of the work on Skittles, and more recently, my graduate students, Rashida Nayem, who has done that last work on the rhythmic cup task. Thank you very much.
Thank you, Dagmar. I think Tamim has a comment and a question. Go on, Tamim.
Okay, please.
Yeah, thank you very much for the nice talk. So it's very impressive actually to find all these parameters with which you can describe such complex tasks in such elegant way. So, but how should I start if I have a new task? So I need you all the time, right?
Yeah.
Or do you have a recipe for how can we address these complex tasks, also balancing and other things? How can the community actually use that in a more general?
So let me maybe and I have a third task where bouncing a ball where we did the very same thing, but the kind of class of tasks that so far we have looked at is really object manipulation, right? And so given that when you start with humans and human arm control, I mean, you can simplify your thinking by making rigid bodies, 2-3 joints, but the assumptions are just horrendous, right? Given the complex skeletal, the muscular system, and multi degrees of freedom. So I really kind of wanted to get away from lumping parameters to understand sensory, motor, muscular dynamics. And I thought, let's really ground ourselves in what we're out there, where we don't make any assumptions. We just look at the physics. The physics, everything's given. Nobody can criticize us, right? That's given. And then incrementally step out and ask, well, for a given task, in the case that I showed, just moving rhythmically back and forth, either with a fixed amplitude or not, what is actually minimally necessary to make this happen? And then without sort of saying, okay, this is it, span the space of parameters. Again, while the control structure, as simple as it is assumed, I set it up without parameter assumptions, simplified amplitude frequency for a rhythmic input, adding an impedance with a stiffness and a damping. So again, you step away from a specific assumption to opening the space of possibilities.
Okay.
So I agree that I'm simplifying it by having an object to concentrate on an object, but I need to sit down and think to actually go towards what you're saying in robotics control. A lot of things don't have an object to start out with, but balance, as you say, and certain trajectories. But it's taken me a while to put all this together. So I'm sure with a little thinking, it can be extended. So I'm happy to chat more.
Okay, thanks.
Right, thank you again. And